So this is a payload called SMART, which stands for Space Measurement of Rocket Release Turbulence. There's actually a bigger team of experimenters involved with this, but for the stuff we're talking about today, it's mostly NASA Goddard and University of Washington who are participating in the sounding rocket portion of the experiment. There are researchers from University of Alaska Fairbanks who are doing some ground-based work for us. So what are we looking at here? We're looking at a key turbulence process called nonlinear scattering. The idea is that lower hybrid waves that are intense enough can scatter into electromagnetic Whistler waves. Before Glenn leaves the room, I will say that this scattering process is going from short wavelength lower hybrid waves to long wavelength Whistler waves. This process has been simulated numerically and in the laboratory, but hasn't been tested in space. So why might this be important? Whistler waves determine the lifetime of energetic particles in the radiation belts. We know that a lot of the VLF Whistler energy at high altitudes is often large enough to be for nonlinear effects to be important, both for lightning-generated Whistlers, plasmaspheric hiss. We don't quite understand the sources for plasmaspheric hiss. There's a lot of variability when you have a substorm in the population of energetic particles that get added. They can enhance, they can be reduced, they can stay the same. When they are enhanced, they can last for a long time or they can dump very quickly. There is some thought that this is due to the wave environment in the radiation belts. What we want to do in our experiment is see the electrostatic lower hybrid waves in the ionosphere and measure the scattered Whistlers that come out. A little bit on the theory here. Over on the left, where you see a blue wave and a red wave coming off, the nonlinear scattering is a wave that's interacting with the particles in the plasma to generate a secondary wave that comes off. The dispersion surface there covers a number of wave modes. Lower hybrid waves are highlighted in one corner. Whistler waves are highlighted in another. There are magnetosonic waves that are also on the same surface. Of importance is that the lowest energy states are when the waves are in the Whistler wave modes. Theoretically, the scattering rate on the bottom here, you see this W, which is the energy in the wave, divided by the energy in the plasma. When that reaches a certain threshold, then this scattering becomes important. Of importance there is that it goes with K perp to the 6th. So as that K gets large, the wavelength gets small for the lower hybrid waves, that scattering becomes very large. One thing to note is this is a vector nonlinearity, so it's very expensive to do simulations in a 3D vector nonlinearity. Over on the right, we see some experiments that were done in the NRL space chamber, where we generate lower hybrid waves with antennas, and as you pump up those lower hybrid waves, you see scattering into the Whistler waves. So to continue on why this might really be important, a VLF wave that enters the upper ionosphere into the plasmasphere, into the radiation belts, it eventually comes to a place where it becomes close to becoming a lower hybrid wave where it damps out. But if the amplitudes are large enough, it can scatter and maintain a smaller K. Sorry, the y-axis got cut and pasted and covered. But the wave vector without scattering gets large, it damps out. With scattering, it stays short, and the one on the bottom is the energy that's in the wave, and so that energy stays up longer and gives you a longer time to have to produce scattering of the energetic particles in the radiation belt. Our experiment is based on some previous experiments that were done, and we generate our lower hybrid turbulence by using a shape charge explosion. There have been many of these experiments done in the 70s. This is a technology that's sort of been lost. I'll describe it a little bit, but we atomize and accelerate barium to velocities between about 8 and 14 kilometers a second. In sunlight, the barium atoms ionize in about 28 seconds. They then start spiraling around the magnetic field, creating what's called an ion ring velocity distribution, which is highly unstable to lower hybrid waves. And then what we want to measure is the whistlers that come off of this. This experiment that was done in the late 70s actually sees waves in the right frequency range, but they were only flying a single electric field sensor and couldn't differentiate between lower hybrid waves and Whistler waves. This is a little cartoon of the entire experiment. We have a 4-stage rocket. We have one of the precious Oriole boosters that we paid for. Let's see if I can get it, there we go. We do all our staging. We tip the rocket over so that we're releasing the barium perpendicular to the magnetic field. This gold thing is our secondary daughter instrumented payload. As you can see, the barium, which is atomic barium, which is green, continues going. It is getting ionized in this 28-second time scale. The blue squiggles represent the lower hybrid waves, and the red squiggles the Whistler waves that go up to the magnetosphere. This is another representation of the entire experiment. We have a bunch of ground-based measurements, and this is a better representation of our instrumented payload. The instrumented payload is primarily dedicated to making plasma wave measurements. We have 3-axis magnetic field measurements and 3-axis vector electric field instrument in sort of the same plane. So in the forward section of this, we have ion Langmuir probes. So we're measuring, if you call that the XY plane, we're measuring all the characteristics of the waves in a coherent XY plane. And then in the Z direction, which would be the spin axis, we have aft electric field booms, and there's one of the search coils is, of course, oriented along the axis of the payload. You'll notice we are doing what are called double-double probes, which are a technique pioneered by Rob Baff. Some of this is designed to look at different wavelengths of the plasma waves. All right, I said this, we're recreating a technology that has somewhat been lost. I do want to thank our friends at Naval Surface Warfare Center, who are our explosive experts. There is 400 pounds of explosives on this payload. a barium liner, the efficiency for getting the barium to high speed is not good. Out of 200 kilograms, we get about 1.5 kilograms of accelerated barium. We're going to be about 1 kilometer away from the barium when it goes off. We have our ACS to orient our measurement payload so that our spin axis along the magnetic field. That allows us to separate parallel and perpendicular electric fields. The 2 waves we're going to be measuring have different characteristics. This task measurement, the 3-axis search coil that Goddard provides, is sort of our key measurement because the whistlers that we're very interested in have a large magnetic field where the electrostatic lower hybrid waves have a very small magnetic field. That will allow us to sort of meet our minimum success of did we see Whistler waves coming off of this. Both these types of waves have large electric fields. This experiment would be hard to do with just electric field measurements. The plasma density fluctuations are small for whistlers and large for lower hybrid waves. The wavelength is large for the electromagnetic whistlers and small for the lower hybrid waves. This is a simulation of the barium release. You're going to see a black dot and a little curve that shows where our payload is in the release. We're only in the very initial part of the release. The fast ion cloud goes out to several hundred kilometers, and we're within basically a kilometer of that. So we're in this really high speed part for the first couple of first few tenths of a second. So a lot of the experiment is accomplished in a very short period of time. We also have some. I don't know if I need you to run the movie that's on the screen. Can you click on the movie on the screen there? There we go. So in the fast jet of barium, there's a phenomenon which is called cycloid bunching. This is because the beam is very narrow at the very beginning, and it's got about a 500-meter ion gyro radius. So only certain ions get to you. They have to be created in exactly the right spot to get to the payload. So there's a lot of dynamics going on in the first few seconds of the release. And you see here that this is showing that in the fast jet that there's a lot of dynamics in when we see payloads that are ions. There's also a slower population that comes out basically thermally from the release. So we're actually doing this test in two different parameter regimes, and the slower barium lasts longer. As I've said, the task instrument is probably our most important measurement. Here's their response curve. We think the lower hybrid waves that are generated will be centered at about 6 kilohertz plus or minus maybe 4 kilohertz or so. I'm not going to play the sound speed or the sound thing for the Whistler waves that were measured on DSX. But the point here is that the Whistler waves we're going to be seeing will be lasting over 30 or 120 seconds, whereas these lightning-generated Whistlers are very, very short-lived, and we think it'll be easy to differentiate between the. There we go. Here's our payload. The forward section you can see down on the left, on the bottom is one of the task coils sort of nestled in among the electric field booms. That forward fiberglass mast is what is used to push the nose cone off, and the aft end is on the right, and we have a resonance probe to measure absolute densities. We have a flux gate magnetometer to look at lower frequency waves, and there's an electron alignment probe in the back also. So I wanted to make a comment about measuring the wavelengths. This is directly from Rob's paper in 1998. In the high-speed jet, we think the wavelengths are going to be about 1 meter, which is a little small for measuring the separations of our sensors. The smallest ones are about 30 centimeters. But you can still get wavelength information, because if you look on the right, on the left here, we take advantage of spin to do this. And you can see that for a plane wave, which is actually what is predicted from the release, on the two sensors that are on the top and bottom, you can get a phase delay for when that wavefront comes to you. And even if you're folding things over, the other plots on the left show what are called a fingerprint. If you look at the spectrum and the wavelength is changing with frequency, you can get a feel for what those wavelengths are. It's going to be a little bit tough to really characterize the 1 meter separations. But I think for the lower speed areas, we think we can look at what we think will be 10-meter lower hybrid waves. University of Alaska is providing some ground-based cameras for us. This is the kinetics mission, and you can see that they can use filtered cameras to give us information on the barium release. The barium neutrals, the brightest line from those are from in the green, and the ions are purple emissions later. So he's telling me I'm almost done. So I wanted to mention one of the problems we've had with this experiment. We're going to launch this experiment in about 2021. When that explosive goes off, you can see on the top left, that casing actually shreds. So the red area is showing that pieces are coming off of that explosive. There are three concerns for safety from that. First, I want to make sure people keep calling this debris. It's not orbital debris. The highest velocity we reach is about 4.5 kilometers a second. So it's not going orbital, but there's sort of three populations. There are really tiny things like sand grains that can go up and hit a satellite and do damage. There's sort of BB-size pellets that could come down and hit maybe an airplane and cause damage to that. And then there are very few large objects that the energy level that they're concerned about is about the energy level of a Major League Baseball pitch, and that could hurt someone if it hit them. We could not convince NASA, and it became a big battle, that one of these larger pieces would not land on a foreign country if we launched from Wallops. And so our launch from Wallops got canceled. We're now going to Wake Island, which is essentially in the middle of nowhere. We'll be camping for 6 weeks to get our launch off. We're scheduled right now for November launch. It looks like we might be delayed slightly again, looks like we may have to do this safety analysis again, because I want to change our orbit, our trajectory just a little bit. But we've run through the process, and we know how to do it. It just takes time to do it when you change the character of all the dispersions that we see from the trajectory. That's it.